Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In the early sessions, we were talking about test of significance and some terminologies related to test of significance was discussed, that is critical region. Determining the critical region at 5% level of significance and 1% level of significance was discussed. So, in this session, in continuance with the topic of critical region, in this session also the discussion will be done about critical region and power of the test of hypothesis. We have discussed about determining the critical region for a particular level of significance alpha is equal to 5% and alpha is equal to 1%. How the critical region will be discussed in general, the critical region depends on the null hypothesis. So, it depends on null hypothesis, test statistics, significance level and the alternative hypothesis. Suppose the null hypothesis is the simple hypothesis H naught mu is equal to mu naught. The test statistic is the standard normal random variable Z assuming H naught is true and the significance level is alpha. So, the test statistic is Z and the significance level is alpha and null hypothesis assumed is H naught mu is equal to mu naught is true. So, the critical region is determined as follows. For the corresponding null hypothesis mu is equal to mu naught, we have HA will be mu less than mu naught or HA will be mu greater than mu naught. The critical region is all of Z less than or equal to Z star, where P of Z less than or equal to Z star is equal to alpha. Just recall in the previous session when alpha is equal to 0.05, we have found out Z star as minus 1.65 and similarly for HA mu greater than mu naught, the critical region is all Z greater than or equal to Z star, where P is probability of Z greater than or equal to Z star is alpha. Just recall again in the previous session when alpha is 5%, this Z star value is plus 1.65. Then talking about two-tailed alternative, that is for HA such that mu not equal to mu naught will be mu greater than mu naught or mu less than mu naught. The critical region is all Z less than or equal to Z star or Z greater than Z star, where Z less than or equal to minus Z star plus Z greater than or equal to Z star will give you alpha, or equivalently singleton we say that P of Z greater than Z star is equal to alpha by 2 because of the symmetricity of the probabilities in standard normal distribution. For example, it was discussed in the previous session with alpha is equal to 5% and these Z star value are 1.96 for alpha is equal to 5% level of significance. Now, how does the significance level and critical region plays a very important role for decision making? The p value of a test means the probability value of the test corresponding to the test statistic will be less than or equal to the significance level alpha precisely when the test value of the test statistic lies in the critical region, that is it lies in the rejection region. Hence, if the test value lies in the critical region, then the null hypothesis is rejected, because it is lying in the rejection region. Null hypothesis will be rejected at the alpha level of significance. If the test value is not in the critical region, then null hypothesis is not rejected, it is accepted. Now we shall work out this example after working out two examples in critical region part. This is the third example, which says that if the test value of the statistic is -2, explain whether null hypothesis is rejected or accepted using the significance levels 0.05 and 0.01. Solution says that we know that in previous example 1 discussed P of Z less than or equal to minus 1.65 is equal to 0.05. And how do you plot this? Z is equal to minus 1.65 and this is the area 0.05 and this is the rejection region of H naught. Therefore, where does your -2 appear here, right? Because now the statistic value is -2. We want to test whether corresponding to this statistic value to -2, whether null hypothesis is accepted or rejected. Now, test hypothesis value is -2 and since it lies in the rejection region, we say that null hypothesis is rejected at 0.05, isn't it? You are asked to explain whether the null hypothesis is rejected or accepted. Here -2 lies in the rejection region. Whenever you draw a line corresponding to -2, the shaded area will be this part, and since it lies in the within 0.05, this is a rejection region called critical region. The explanation goes like that: since Z is equal to -2 is less than minus 1.65 and it lies in the critical region, therefore H naught is rejected at alpha is equal to 0.05 when the statistic value is Z is equal to -2. You are also asked to test whether the null hypothesis is rejected or accepted at 0.01. So, for the corresponding to 0.01 as discussed in example 2, that is P of Z less than or equal to minus 2.33 is equal to 0.01, isn't it? Another diagram for 1% level of significance. This area, this is 0.01 and this is minus 2.33. Z is equal to, now Z is equal to -2 lies here, our statistic value, and since it is not in the rejection region, H naught will not be rejected. Since it is not lying in the critical region corresponding to 1% level of significance, H naught is not rejected. In the sense, H naught is accepted when Z is equal to -2 at 1% level of significance. The explanation goes like that: the critical region for the standard normal random variable at 0.05 level of significance for the alternative hypothesis HA mu less than mu naught is all values Z less than or equal to minus 1.65, and as shown in the diagram, -2 is less than minus 1.65, therefore null hypothesis is rejected at 0.05 significance level. However, the critical region at 0.01 level of significance is all values less than or equal to minus 2.33, and since -2 is not less than minus 2.33 as discussed in the diagram, -2 lies outside the critical region, therefore null hypothesis is not rejected at 0.01 significance level, it is accepted at 1% level of significance. So, after working out an example relating to the decision making of based on critical region and level of significance, we shall discuss this type 1 and type 2 errors. We have seen the exact definition of type 1 and type 2 errors in the previous session when we were discussing the terminologies related to test of significance. Now, here it is revisited because of finding the probability of type 1 and type 2 error. There are two types of mistakes that can be made when reaching a decision on the basis of hypothesis test, that is rejecting the null hypothesis when it is true, which is called type 1 error, and it is called producer's risk, and not rejecting the null hypothesis, in the sense accepting the null hypothesis when it is false, when the alternative hypothesis is true. When the alternative hypothesis is true means null hypothesis is false. Okay. Each type of error depends on the specified significance level. How does the errors and levels correlate to each other, we shall see. Okay. So, give an illustration to type 1 error. Suppose the significance level were chosen to be 0.05 and the p value of the statistic is 0.0228. This is the assumption made, that is, the level of significance is 0.05 and the test value of the statistic is 0.0228 and 0.0228 is less than 0.05. When you draw the diagram, you just see area 0.0228 is contained in the area of 0.05 when shaded. So, H naught would be rejected at the 0.05 level of significance. Okay. However, this would be a mistake when H naught is rejected, when H naught is true, is a mistake. That error is called type 1 error. Okay. So, the example which we are giving for type 1 error is the significance level is 0.05 and if test value is 0.0228, H naught will be automatically rejected because the statistic value lies in the critical region, but although it is automatically rejected, when it is true, it is a mistake. So, that mistake is called type 1 error. So, let me draw the diagram and show you. This is 0.05 area totally shaded, and if you take this area, this will be 0.0228. So, you can see 0.0228, that is 2.28 percentage area totally contained in 5 percentage area. This value is actually z is equal to minus 1.65. Okay. Since 0.0228 is lesser to 0.05 and you can see the area is totally lying in the critical region. Critical region means rejection region, therefore, H naught will be rejected automatically. When H naught is rejected, actually when it is true, it is a mistake and it is called type 1 error. This is the illustration which we are giving for type 1 error. Since it leads to the rejection, there is always a chance. Okay. So, what is the probability of type 1 error is if a simple hypothesis such as H naught mu is equal to mu naught is in fact true, then all values of this test statistic in the critical region will result in a type 1 error. Okay. Because in the critical region of type 1 error, H naught is rejected, therefore, H naught being assumed as true is called values of the test statistic. Since the significance level alpha is the probability test statistic will lie in the critical region, it follows that alpha is the probability of making a type 1 error. When the error occurs and since it is a chance, what is the probability of occurrence of type 1 error means it is nothing but the significance level alpha. Let us see this example. Suppose the null hypothesis is H naught such that mu is equal to mu naught and the significance level is chosen to be 0.05, then the critical region consists of all values of the standard normal random variable less than or equal to minus 1.65. The probability that test value will lie to the left of minus 1.65 is precisely 0.05. This is an example showing probability of type 1 error. Okay. So, this is z is equal to minus 1.65 and this area is 0.05. Here H naught is true and it is rejected. Next, probability of type 2 error. Type 1 error is rejecting H naught when it is true. Type 2 error is accepting H naught when it is false, that is not accepting H naught when alternative hypothesis is true. In the sense, a type 2 error results if we fail to reject the null hypothesis when the alternative hypothesis is true. That is, you just have to carefully read fail to reject in the sense accepting the when the null hypothesis is false. So, you just coin the words like if fail to reject the null hypothesis when the alternative hypothesis is true. Okay. Now, a composite alternative hypothesis, composite in the sense H A such that mu is not equal to mu naught. Mu not equal to mu naught, there are two possibilities, mu greater than mu naught and mu less than mu naught. That type of alternative hypothesis is called composite alternative hypothesis, does not specify a particular value of the parameter that forms the basis of the test. Okay. And therefore, does not uniquely determine the distribution of the underlying random variable. We cannot say what distribution the particular random variable follows. Hence, we cannot determine the probability of a type 2 error by assuming the alternative hypothesis is true. Whereas, we can determine the probability of type 1 error by assuming null hypothesis is true. We cannot determine the probability of type 2 error because the distribution is not unique. Okay. Next, after discussing about the critical region and levels of significance, next terminology we are going to discuss is power of a test. Suppose that null and alternative hypotheses are hypotheses. There are two types of hypotheses, they are called hypotheses about a parameter, say the mean mu of a random variable x whose value completely determines the distribution of x. The test is to be conducted at a specified level of significance alpha, which therefore determines a critical region for the test statistic. This only decides whether we have to accept H naught or reject H naught. Now, let the mu 1 be a specific value of the parameter mu. Then, the power of the test at mu 1 denoted by k of mu 1 is defined to be the probability that the null hypothesis H naught mu is equal to mu naught will be rejected when mu is equal to mu 1. Therefore, 1 minus k of mu 1 is the probability of type 2 error given that mu is equal to mu 1 which is not equal to mu naught. Mu 1 is not equal to mu naught. Mu 1 is a new value of mu naught other than mu naught, and where k of mu 1 is the probability that the test statistic lies in the critical region given that mu is equal to mu 1. Okay. So, the power of the test is k of mu 1. It is actually the probability that null hypothesis will be rejected when mu is equal to mu 1, because H naught is such that mu is equal to mu naught is taken to be true and it will be rejected when you take mu is equal to mu 1. Okay, just recall the critical region for the test statistic. For the parameter mu, the corresponding test statistic sample statistic is x bar, and the corresponding standard normal variable for x bar is x bar minus mu naught divided by sigma by root n, is determined under this assumption that this statistic is not standard normal random variable. So, the probability that it lies in the critical region is not equal to the alpha, that is, it is not probability of type 1 error. Okay, just see this example of how the power of the test is computed. Just imagine that suppose that null hypothesis is such that mu is equal to 12. This is your mu naught value. This is to be tested against alternative hypothesis HA mu less than 12 at 0.05 level of significance based on a random sample of size 36. Suppose that mu value is reduced from 12 to 11. This is your new mu 1 value. This is mu naught and this is mu 1, and the standard deviation is still 3. What is the power k of 11 of the test? Okay. We shall see this given H naught such that mu is equal to 12. This is your mu naught value, and 12 is reduced to 11. This is your mu 1 value 11. You are asked to find out the power k of 11 of the test. Now, the random variable says the test statistic of the random variable bar is z is equal to x bar minus mu divided by sigma by root n, where x bar is the sample mean and mu is mu naught is equal to 12, sigma is 3 standard deviation, n is equal to, what is n value? 36. Substitute all these values, then z is equal to x bar minus 12 by 0.5 and you are having p of z less than or equal to minus 1.65 is equal to 0.05. Therefore, substituting for z, x bar minus 12 by 0.5 is less than or equal to minus 1.65 is your level of significance alpha, but that is what is power of the test. Okay. So, power of the test is this equal to p of x bar is less than or equal to minus 1.65 into 0.5, this minus 12 goes to that side, it is plus 12. Okay. Now, this 12 is now changed to 11. How? The variable will change, p of x bar minus 11 by 0.5 is less than or equal to minus 1.65 into 0.5 plus 12 minus 11, the whole thing by 0.5. Okay. K of 11 is equal to p of x bar minus 11 by 0.5, which is p of z is less than or equal to 0.35. Okay. Just draw the diagram. Where does p of z less than or equal to 0.5 comes? This is z is equal to 0.35. Plot it on the diagram of standard normal distribution curve, z is equal to 0, then shade the whole area. Shade the whole area. Standard normal distribution table given here will give you the value from 0 to 0.35. Therefore, this area is already 0.5. Just we will see this area from the tables. We want corresponding to 0.3 and 0.5. This is 0.1368. Just zoom it and see. This is 0.3, 0.3 and then 0.05. This is the value 0.16, just see 0.3 and 0.5. This is the value 0.1368. It gives you the value from z is equal to 0 to z is equal to 0.35. Okay. 0.1368, isn't it? This area value is 0.1368 and this is already 0.5. So, the answer is 0.5 plus 0.1368 is equal to 0.6368. This is the power of the test statistic. In this session, discussion about critical region, power of the test and relationship between type 1 and type 2 error, the level of significance has been done. Also, some problems have been worked out in finding the power of the test and illustrations of type 1 and type 2 error are also given. So, based on the discussion in this session, the following questions are posed. What is meant by power of the test? Explain how will you determine critical region in general, whereas in particular 5% level of significance and 1% level of significance we have seen in the previous session. So, how will you determine the critical region in general for alpha? How will you relate type 1 and type 2 errors with levels of significance? Thank you.